Hey, today I'm going to be talking about side channel attacks on secure systems. Let's start by talking a little bit about what a side channel attack is. So, these are a little bit different than traditional attacks, um, where traditional attacks attack flaws in the design or some kind of algorithm for example, a crypto system or some kind of setup. A side channel attack instead attacks fundamental oversights and implementations of this crypto system. And these can compromise secure algorithms, for example, by deducing the key values that were used for some encryptions. Some common types of side channel attacks are timing attacks, which are based on measuring how much time different computations take, power attacks, which are based on measuring how much power different computations draw, and electromagnetic attacks, which are based on performing signal analysis on leaked electromagnetic radiation, and finally, cache attacks, which are based on monitoring cache accesses made by users in shared physical systems. So today, we're going to walk through an example of a timing attack. This example draws from a challenge that I wrote for RITSec CTF that was a few weeks ago. And here's a simplified description of the challenge. So basically, we're given a tool that performs modular exponentiation for RSA encryption. The results of the exponentiation are encrypted using AES with a secret key. The encryption exponent for RSA is 32 bits and it's stored in the exponentiation tool. We can choose a slice of the exponent to use, starting from the least significant bit. For example, we can choose any number from 1 to 32, and if we do 1, we'll just have the rightmost bit, 2 is the rightmost 2 bits, and so on and so forth. And finally, we're also given the encryption modulus n for RSA and 3 RSA ciphertexts. So a couple things that we might notice here. First, n is fairly small, so we can factor it into its component primes, p and q. That should be pretty trivial because of how small n is. Additionally, because of that second bullet there, the results are encrypted using AES with a secret key. That means that we can't actually use the results of the exponentiation. So we can't figure out what those numbers are when we put in a base and a slice. We can't figure out what the result is. So that gives us a little clue that we have to do something a little different, that we're not attacking the actual algorithm, but something that reveals information in its implementation. And that's where the timing attack comes in. So why don't we start by taking a little look at some of the source code for this exponentiation tool. And this is the heart of it. It does the exponentiation. And if you explore it for a second, you'll notice that this is similar to, it's an implementation of a square and multiply algorithm. And all this means is that we convert the exponent to binary, read it from the least to most significant bit, so that's right to left. Our starting number is 1, and for each 0 bit that we read in the exponent, we square our current number. And for each 1 bit we read, we square the current number and multiply by the original base that we have. So what you might notice here is that for each 0 bit we encounter, we only have to do one operation. That's one multiply, where we're squaring the current number. So we multiply the current number by itself. But each 1 bit we encounter is 2 operations, because we square the current number and multiply by the original base. That's 2 multiplies. And so every time we encounter a 1 bit, that's going to take a little bit more time to compute than a 0 bit. In fact, if you take a look at the source code here, we see that result equals result times result. That line will always be executed, but only if e mod 2 is 1, and that means that the rightmost bit is a 1, will we do that extra multiplication. Okay? So to think about our attack, realize that we can choose how many bits of the exponent we use, because we have that little slice functionality that allows us to take any number of bits starting from the least significant and going leftward. Also, we know that on average, 1s are probably going to take twice as long as 0s because we have 2 multiplies versus just 1. So the general process of our attack should be that we iterate from 1 to the number of bits in the exponent and see how much time each of those computations takes. So to get any useful information out of this, we should take the difference in the number, how much time it takes to do a certain number of bits, uh, and the difference between that and how much time it took to do that computation, but with one fewer bit. And the reason we do that is because when we have a greater difference, that means that new extra bit that we added from the previous attempt is going to be a 1 because we have a greater difference in time. So it took a little bit more extra time. And if it's a smaller difference, that means that it took less extra time. And so that bit is probably 0. So again, to simplify, instead of, because the tool isn't hosted anymore, that CTF was a few weeks ago, we're just using this function called oracle, where we put in the base and the size of the slice of the exponent that we're using. And now part of our attack code here would just be iterating from like the smallest possible slice size to the largest, and we're taking account of how much time each of that took. And then we're basically counting the differences from 1 to the previous time. Okay, and then when we plot all these differences, we get something that looks like this. And you can see there are clear peaks and valleys in here. And if we think about this, these probably correspond to 1s and 0s. So if we threshold these values, and here we just have to pick a value that, makes sense to us. So if we threshold, for example, like this, we'll get a sequence of 0s and 1s. Now, the first thing to note is that these are in backwards order because the smallest slice size is starting from the least significant bit, and that's represented on the left side of the diagram here. But when we write out the exponent in binary, the least significant bit is always on the rightmost side. That's the 2 to the 0 bit. Okay, another thing to notice is that for the least significant bit, you'll see we have a question mark there. That's all the way on the left side of that graph. That's because we don't immediately know whether that's a 0 or 1 because we don't have anything to compare it to. So we don't have a difference that we can take because that's the first one that we do. But even with that small bit of uncertainty, this is still way better than having no information about the exponent, because here we're basically given only 2 possibilities for what this exponent could be, whether that last bit is a 0 or a 1. Those are the only 2 possibilities, versus 2 to the 32 possibilities as it would be if we had no information about this. And we could also, we could just try both of them, or we could, use some information about the time to figure out whether that's a 0 or 1. And in the end, we end up with this exponent, which corresponds to, like in binary, corresponds to that number in decimal. And from here, we can easily decrypt the ciphertext because we can figure out the decryption exponent and then raise the ciphertext to that exponent to get the plaintext. Okay, let's talk for a second about how we might secure against these types of attacks. So another important instance of a timing attack is comparing password hashes in a database. So when you think about when you enter a password in, it takes the hash of it and compares that hash against what the expected password hash should be. And when you think about comparing hashes, which are basically just fixed length strings, the way to do that is probably that you start from the leftmost character in both hashes, and if it's the same, then you move to the next character in both hashes. And if that's the same, then you move to the next one, and then once you find a difference, you return, oh, this is the wrong password. Or if you reach the end of both and you haven't found a difference, then you return, oh, this was the correct password. But notice here that a hash that is more correct than something else, than another hash, is going to take more time in this comparison because you're going to compare more of the characters than you will. For example, if the first character of the hash is wrong, it's immediately going to return. But if the first 3 characters are correct, it's going to compare the first 3, and then it's only going to return after comparing the 4th one. And so then you can sort of maybe brute force and get more information about what this password could be. So to secure against this, you could require, for example, every API call or every comparison in the database to take the same amount of time. That is, it's constant time independent of the input. So for example, if we have a base time of 0.005 seconds, and we do this computation and it hasn't been 0.005 seconds yet, we wait until it has reached that amount of time, and then we return, so that every computation takes roughly the same amount of time, and you can't get any information given just how much time these take. Okay, now to conclude, in summary, we talked about the basics of side channel attacks, different types of side channel attacks, an example of a timing attack, and one possible way of defending against timing attacks. Beyond this is exploring other types of side channel attacks, how they work, and examining how to secure systems against them. Here are some of the references I used, and thank you for watching.